Okay, so now we're at a state where we can look at applying the method of averaging. Okay, so now we'll go through this relatively quickly, since we're already familiar with this from the previous lecture. If you haven't watched a lecture on laminar dispersion yet, you have to go and watch that first and then come back and pick up from this point. Okay, so the first stage in the method of averaging is to decompose the concentration, right, as the cross-section average concentration plus C tilde. So this of course denotes the deviation from the average, right? So by definition, the cross-section average of C tilde is 0, right? And we know that the definition of this C tilde is similar to what we use for the velocity, where there's two factors, a normalization. Okay, so this was the first step, right, to decompose the concentration. The second step is to take the average of equation 1. So we average out, apply the averaging operator onto equation 1 itself, onto this PDE. Okay, before I continue, just as a point of recollection, remember we cannot apply the method of perturbation directly for small p, right? Because if we assume a perturbation expansion directly into equation 1, we'll see that at 0th order we simply get C is equal to an arbitrary unknown constant, because these boundary conditions do not allow us to solve the 0th order problem definitely. Instead, we just get an arbitrary constant which we cannot solve for at that order, and that's a sure signal that you can apply this method of averaging, and that's how we introduce the procedure at this course without going into more detail. Yeah, this is what we saw in some more detail in the previous lecture on laminar dispersion. Okay, so and this condition of course is important because it is what's going to allow us to obtain the correction C tilde later, as we shall see. Okay, so again, taking the average of equation 1, which is the second step, right, of the averaging procedure, we get the following. So we have, let's look at the LHS of equation 1. If we apply the average, you have Petley number times the averaging operator acting on. So I took u into the derivative of x because u is of course independent of x. Now because this averaging operator is an integral of on R, I can take the derivative of x out of the averaging operator. Of UC, and now this term I'm going to define as being equal to the cup mixing average. Sorry, I'm going to define as this being equal to the cup mixing average times the average velocity, where this cup mixing average is defined as RC. So it's like the cross section average, but I'm going to weight it by the velocity u, right? And then to normalize, I have to also account for sorry, I keep making this mistake. It's not 0 to R, it's 0 to 1. Right, U R dr, and this is nothing but the mean concentration. So a quick point of order here. In the previous lecture, laminar dispersion, I forgot this denominator factor. This denominator factor, of course, is just the mean U bar. So you will find a U bar missing, a denominator normalization missing from the CM in the previous lecture, but otherwise everything is the same. So if you just go back to that and maybe take a quick look at that later on to make sure, I mean, that's the only way of also the dimensions of the problem will balance correctly. Okay, so let's carry on now correctly in this lecture, and then you can always go back and make sure you understand where we had missed out this factor in the previous lecture. Okay, so that means this term now takes the form of P average velocity ddx of the cup mixing average. So again, the physical meaning of the cup mixing average is that it's the average that you get if you collect the fluid coming out. Let's say you have a pipe at a certain distance x, you cut a section of that pipe, you collect the fluid that comes through that, the flux of material that is that flows out of that through that section in a certain time interval, stir up that mixture and then look at the average, the mean concentration of that mixture, you get the cup mixing average. So it's an average that's weighted by the amount of axial flux, or a axial flux weighted average, whereas the cross section average is the actual values of the concentration across the cross section and not based on the flux of material through that cross section. So you can already see from the definition that the cup mixing average becomes equal to this cross section average we have here if u is independent of r, because then I can take the u out common from both these terms, cancel it out, and then I get back my usual cup mixing average. I get back my cross section average. So we can already see here that Cm is equal to C if u is a constant or independent of r. Okay, so this is going to be important in a second. So anyway, so let's stop here. This is the left hand term. Let's look at the right hand side. So after averaging out, so now the right hand side involves applying the averaging on both these terms. The first term, as we saw in the previous lecture, goes to 0, right? Because if I take the integral of r multiplying this term, the r will cancel out with this denominator r. Applying the integral takes off this derivative, and instead I have to evaluate r dc dr at the two limits 0 and 1. Now this term at r equal to 0 is 0 because of this r factor, and at r equal to 1 is 0 because of the boundary condition on the dc by dr term. So this entire diffusion term gets knocked off by the averaging operator, and I'm just left with the average of this reaction rate term. Now treating that term was trivial in the case of the unsteady laminar dispersion problem, because I just took the averaging operator into the time derivative. Here I can't do that as simply. So let's see how to proceed. So 0 comes out of acting the averaging on the diffusion operator, but I get a term from the reaction rate which looks like this. Okay, now ideally what I want to do is I want to take the averaging operator into the function r and apply it on C. But how can I do it without specifying the form of RC? Well, I can use the fact that I can use a Taylor series expansion based on the idea that C can be written, of course, as cross section average plus C tilde, where I should note here that C tilde we expect to be much smaller than the C average. In fact, we'll see C average is order 1 and C tilde is order P as we proceed with the calculation. Okay, so under that idea, I'm going to write this as minus Peckley Darmkohler R of C average plus C tilde, right? And I'm then going to use a Taylor series expansion here. Right, so this is R acting on the cross section average. So this is actually now independent of R, so I could take it out eventually from the averaging operator, right? Or the average of a constant is just a constant. So this is the first term. Then I have the second term of the, the next term of the Taylor series, which is just C tilde R prime. So dr by d of the argument, but evaluated at C average, right? Because I'm applying the Taylor series about C average. And then I have the next order term. You'll see why I'm going to the next order in a second. And I'm going to stop here, plus order of C tilde cube and so on. Okay, and this is going to be now approximately equal to, so I can put the approximate sign here as well, times, I'll have R of C coming out of the averaging operator because it's just independent of R, right? Because it's the reaction rate evaluated at the cross section average, there is no R dependence. This has an R dependence, but the averaging operator applied on C tilde, right, this is 0. by definition, right? Because the C tilde is deviations from the average. But the average of C tilde square is certainly not 0, right? So this is a non-zero term, so we have to retain this term. Okay, so the net result we get is it's Peclet-Darmkohler, and up to second order in epsilon, which is the order of P, we can write it in the following fashion. Okay, so this is why, so now bear in mind that this is the only correction term I get by averaging the reaction rate, and it only survives if my reaction rate is at least second order kinetics. If I have a first order reaction rate R, then R double prime will be 0, right? So if R is equal to K, if R is equal to just C, right, then the first derivative exists, but the second derivative is 0, and I won't have this correction term. So for a first order kinetics reaction, the average of the reaction rate is the same as the reaction rate evaluated at the cross-section average. But that is not true if you have second order kinetics or higher, and then you get corrections which has to account for the effect of the deviations of the concentration from the average value on the net reaction rate. So that's important to bear in mind. So let us write down now the averaged equation. So what do I have by combining both sides? So the Peclet can be cancelled from both sides. Right, where I've stopped, of course, as we shall see later, this is up to order of these cube and higher terms I have dropped at this point. But we can even ignore this last point. So I have already explained to what order I stopped above. So let's just stop here. Okay, so now before we proceed, can we see now how we can go back to the PFR model right from here? So we have an averaged equation now, but this equation isn't closed because I don't know how Cm is related to C cross-section average. In fact, the relation of the two, as we saw in the previous lecture, involves determining C tilde. In addition, we also have C tilde explicitly in this expression. But we do know now that if Peclet goes to 0, I expect Cm to be equal to cross-section average, right? And I expect C tilde to be 0. So then I get the PFR model, right? So if Peclet goes to 0, basically there's no variation of the concentration across the cross-section. Consequently, Cm is equal to C bar is equal to some constant. So I can replace Cm by just C cross-section average here. Also C tilde is 0, so this term is gone off, and what I will get is exactly the PFR model. So this was the first limit we already identified here at the beginning, that if P is 0, I get a PFR model in perfect radial mixing. But I now have another way to get the PFR. If P is not equal to 0, so I have P not equal to 0, and however I have U equal to a constant, then I can show, of course, as I described here, right, that if U is constant, Cm is still the cross-section average, but of course C tilde is not 0, right? So only for R double prime of C equal to 0, I get the PFR model, right? So in other words, there are two ways to get a effective ideal plug flow reactor model, to be an accurate description. The first is where you have perfect radial mixing and truly no concentration variations in the radial direction. Then a PFR model is appropriate for any reaction kinetics. If you do have concentration variations in the radial direction which are non-negligible, that means the axial Peclet number is not vanishingly small, but you have a plug flow profile as in a electro-osmotic type flow or a strongly turbulent flow, then you can say still that the Cupping mixing average is same as the cross-section average. So this term becomes the same as what you have in the PFR. However, the reaction rate term introduces corrections unless you have a first order kinetics. So a tubular reactor with a plug flow velocity profile and supporting a first order kinetics reaction can be described by a plug flow model even if you don't have perfect radial mixing. However, if you have a second order reaction or higher, the plug flow model will have errors. So you see how this is a new limit or a new way to get the plug flow model that was not obvious at least heuristically from the original equations, but this analysis has made it clear even at this stage without solving the problem. So again, you see how these asymptotic procedures can give you lots of insights even before you solve the problem or look at any detailed results. Okay, so let's call this equation now equation 2 probably. No, actually I should call the equation I wrote down for the decomposition as 2, right? So this is equation 2, which makes this now equation 3. So this is the averaged equation. So the last step is now we need to find C tilde as a function of C bar perturbatively, right? Because we cannot find it exactly, otherwise, as I said earlier, we can solve this problem exactly. The entire problem would be solvable if it was possible to do that. So instead we resort to a perturbation series and we write C tilde as C tilde naught plus Peclet number C tilde 1 plus Peclet square C tilde 2 plus higher order terms which we shall neglect. Okay, now again at order 1, like we saw in the previous lecture, we will see C tilde is equal to 0, right? Because in fact we have this condition from equation 2, right, which is the normalization condition in the way we decompose the concentration, that the cross-section average of these deviations from the average are themselves 0. So the equation, of course, at order 1 will just give us a diffusion operator equal to 0, right? Of course, so this is I forgot to mention, this is now substituted in, of course, the full model 1. Right, so substituting in 1, at order 1 we'll just get 1 by r d by dr of r d c naught tilde by dr equal to 0. This will tell us that c naught tilde is some constant, but with the boundary conditions, of course, of no flux and boundedness. And then when we apply this normalization condition, we will find that the 0th order term or the order 1 term for the for c tilde is just 0. This we already expected, because remember we said that C tilde is going to be less than the cross-section average. So this is going to be an order epsilon term and smaller, whereas this is an order 1 term. Okay, this is similar to the previous lecture. So proceeding, we now go to order P. So we now have 1 by r dou by dou r of r dou c 1 tilde by dou r is equal to, now remember we have to substitute, let's go back here, where is my equation 1? Yes. So what we are doing is we are substituting C is equal to cross section average plus C tilde, and then for C tilde we put in the perturbation expansion. So this term we've already dealt with. Coming here we see that this is the order Peclet term, So we will get only the first order contribution, or the zeroth order contribution from here, which is u ddx of cross section average plus c tilde naught, but c tilde naught is 0, so only the cross section average comes here. And similarly, the rate of r applied at c, we can again replace c as cross section average plus c tilde, and then use a Taylor series expansion here like we did when we obtained the averaged equation. So I leave that as an exercise for you to do and just write out the result here. So at order 1 we find you'll only get u, right, all the c tilde at 0 contributions, this term is going to go to 0, right. Okay, now I can use equation 3 here, right, because I know that I can use 3 yes. So what I want to do now is ddx of the cross section average is a constant, is independent of the radial direction, but I would like to write it in terms of the reaction rate. In other words, I want to use this averaged equation to further simplify what I'm obtaining here, right. We did something similar when we replaced the time derivative term in the laminar dispersion problem by the convection term. So here we're going to replace the convection term in terms of the reaction rate term, so that we get a simplified result. So to do that, we have to look at a modified form of 3. So I can write this as remember, if you go back to the fact that this is simply uc, I can write this as where u tilde is the deviation of u from its average. Right, so this can be written as these two products. Why? Because if I have the other terms such as u tilde cross section average of c will go to 0 because the average of u tilde is 0. So the only terms that survive are these two. Right, this is because is 0. Okay, and so then this means that therefore from 3 I have the fact that ddx okay, so you can make sure that you get the same thing. Remember, again, I replaced c by c cross average plus c tilde and use a Taylor series to get these terms. Okay, so this just derives from 3, and now I can use this here in this order 1 expansion. So this was a little detour. So coming back here and using this expression to replace this term at order 1, you will see that I get the following equation. Okay, so now I've written down the right hand side entirely in terms of the reaction rate term, and I've eliminated this convection rated term, eliminated this convection related term using the averaged equation 3. Right, so it allowed for some simplification. Okay, so now this of course is a constant term. Damkohler number times the rate is independent of r. This only depends on x and time, or in x in our problem. but u depends on r, so we'll have to carry out two nested integrations to obtain C1 by applying the boundary conditions on C1, of course, which are, sorry, this is tilde. So dou C1 tilde by dou r at 1 is equal to 0. Of course, C1 tilde at r equal to 0 is bounded. Right, and of course finally you have the extra normalization which we need always to find a definite solution. And our result, which I'll leave the calculation up to you, it's quite simple. You will find it is the following. This is very similar to, I think, what we obtained in the previous lecture. So this is my correction at order 1. Let me now go to order p squared. Okay, so the right hand side is the same as before. The diffusion operator from equation 1 just yields the following for the right hand side. But then the convection term now has to be treated carefully. So again, if we go back up here for the full model, I'll have this u dc by dx. So I have u d cross section average c plus c tilde. Now I rewrote that cross section average, so I get two terms, right? One is u ddx of c tilde, the other is u ddx of c cross section average. But u ddx of c cross section average I can rewrite using this, right? So u ddx of cross section average is u by cross section average times all of this stuff. So from here I can also extract the order p square terms, right? If you write this all down and do it carefully, you can show that you get the following result. So C1 tilde is coming from here at this previous order, plus u ddx of again C1 tilde, this comes from the original equation, plus Damkohler number C1 tilde r prime of C. So you note here you get R1 prime here because you have not taken the average of this term. This is coming from applying the Taylor series to the reaction rate term here in equation 1, right? So you do get R prime C tilde, whereas that term was lost when you apply the Taylor series while taking the average of the equation, because the average of C tilde was 0. So you didn't have it here, but you will obtain it here. Okay, now you will see that these terms, right, both of these terms involve ddx of C1 tilde, right? So both of these terms inadvertently give you ddx of C1 tilde, which means you'll get ddx of Damkohler number times R of C. So I use this following fact that ddx of R of C, right, we would like to take the derivative inside. This can be written as the Damkohler, sorry, there's no Damkohler, so I'm just trying to derive an identity here. So this can be written using the chain rule as R prime of C times dc bar by dx. Right, and this ddx of the cross section average in turn can be replaced by this, right? But since I am retaining only the leading order terms, I'll only retain the reading order contribution from here, right? So this c tilde and c tilde square, if I substitute in here, will take those contributions will go to order Peckley cube, which I am not interested in. So the only leading order contribution for dc cross average by dx is just coming from here. This is an order 1 term. These are both low orders. So this will become okay, so this I can use as an identity, and then you can show that my equation ultimately or the result. I'll just give you the result directly. So you'll get the equation for C2 tilde, and then you solve it again by 2 integrations and applying the corresponding boundary conditions, which are the same as for C1 tilde, and you get the following result.